I'm Mikael Vidstedt. I work at Oracle. I've been working with JVMs. Like you said, you've been on the other side of the table. It strikes me that I've never actually applied for a job. I came into the startup in Stockholm back in 2000, and then like later I ended up in the US. But it's always been JVMs. It's been 3 different companies. Now I'm at Oracle. Love JVMs. Love the technology. Safe harbor slide, everything I'm about to say is a lie. Here's the agenda. So I'm going to talk about containers and Java. I'm going to talk something like high level about Docker, but since we covered part of it, I'm going to try to keep that part short. I'm going to talk a bit about creating custom JREs. This is new functionality that we introduced in JDK 9, also known as Jigsaw. It does gel pretty nicely with Docker and containers in general. I'm going to say something about images and how you can create your own and how you can optimize their respective sizes, which may or may not be important depending on your use cases. And then I'm going to say something about what we have done on the Java side specifically for Docker or containers in general. So let's start on a high level. In a world of containers like Docker, and I should say from the very start here that I will say Docker a lot, and it's not really important that it's Docker. It's more like there are many different container technologies. They all, or at least most of them, use the same operating system level functionality in the end, but Docker has become this sort of term we use to describe all of that technology. So this is true from the JVM perspective as well. We don't actually care that it's Docker, but there is functionality in the Linux kernel and in the Linux user space that we make use of, and that is sort of surfaced through Docker. So in a world of containers, we expect safety and security to become increasingly more important. So this, I think, the world as a whole right now, we're sort of slowly getting more and more security concerned, and we're taking care of that more and more as a world, I'm going to say, which I think is a really good thing. But I think it is becoming more important, and I think we're going to see security issues in our industry for all eternity, I guess. Still trying to get over the Spectre part from early this year. We're also expecting to see sprawl, and what I mean by sprawl is anything that has to do with the environment you're now running in is not heterogeneous anymore. You have homogeneous anymore. You don't have the same types of machines, the same configuration, the same latencies across the network, all of that. So everything will sort of be different. So when you run your thing, as much as the container world is trying to isolate and provide you with a sort of an idealized environment, there are still going to be differences in where you get deployed. So that's important to sort of take into account and keep in mind. This is not an exhaustive list in any way, but we like to think that Java is really well positioned as a runtime for these types of environments. It's everything from the fact that it's a managed runtime and language, so you can provoke null pointers, but it's at least not going to crash your process. Working on it. We do have Java obviously we can run on all the different operating systems and CPU architectures and all of that. It's agnostic from that point of view. This safety is being enforced by the JVM and so on and so forth. There are a number of different reasons why we believe that Java is good for this environment. And maybe most importantly of all, we do recognize that this is really important to us. So we are committed to keep the investment going in this area and make sure that Java continues to be a really good citizen. Who here has actually used Docker? Okay, bunch of hands. Who has created a Java-based Docker image with Java in it? Okay, a few hands. So Docker is obviously a few different things, but I think we did see or hear about the concept of images. It's also a company and a Docker hub where you can store your images and stuff like that. I'd like to give a really quick demo of this. In the end, got black. So here's what it could look like. So if you want to create your own Docker image, let's start there. So Docker image, we heard about it. It's a way to package your application, to take all the dependencies it has, all the configuration, all that, and bake it into one single file so that later when you deploy it, you know that it's going to work because it's isolated, it's self-contained. If you want to create a really simple Docker image, and I'll just show this quickly because some of the later parts of this presentation sort of builds on that, you at least have an idea of what it contains. You could start with something like this. You need 3 files. You need the JDK. So in this case, I've downloaded the most recent version of JDK 11, the one we released less than a month ago. Is it? Well, yeah, it is. You need your application, in this case, Hello World, and you need a Docker file. And if we have a look at what's inside of that Docker file, you'll see a few different lines. So let me do that. So on line 1, we're saying we need to base it on something. We have the JDK, but it still needs to run on something. In this case, I'm picking up Oracle Linux because I work at Oracle. If you want to use your other favorite Linux distribution, please go ahead and do so. We're saying take the JDK and put it inside of this image. So now we have the base image with the operating system stuff in it. We have the JDK. I installed it in the opt.jdk directory. Turns out that this file, by the way, contains a directory called JDK 11. So the end result is that the JDK, the Java home variable, so to speak, if you're familiar with that, will be under opt.jdk JDK 11. I set up a work there. I'm not going to go into that. I add my application. So now we have the base image, Java, the JDK, and your app on top of that. I also set up the path, and then I finally say, when you start this, run Java show version hello world.java. And some of you may be confused here. How can you run hello world.java? So this is actually new functionality in JDK 11. So if I do something like this, do I have a Java 11 here? Yes, I do. I can actually do this now. And yay! So this is new functionality. It's something we introduced for making it easier to start playing around with Java. So if you have a single class with, in this case, Hello World, it looks exactly like somebody else showed Hello World. So if you have this and you run it, it's going to run main automatically. You don't need to do Java C first. So, okay. So let's go ahead and actually build this thing. And I'm going to say Docker build, and I'm going to call the image, or call the tag, the image that is created with the name test. So this is now something you can do ahead of time, minutes before you deploy, hours before you deploy, years before you deploy. It's baked in, it's there, it's ready to go. It's a file on disk, and it describes what should happen when I actually run this later. So later, when I come back and I actually really do want to run Hello World, I'll do run, and I'll say, just do that for completeness. So I'll say container run, and lo and behold, it runs the show version, and it runs Hello World, and it sort of does what you'd expect, I guess. So obviously you can make this example much more complicated, but this is sort of the simplest possible example, I guess, of how to package a Java application in a Docker image. Made sense? Next show of hands. How many people here are running Java 1? Let's start with 1.4, to be generous. Uh-oh.
I wanted to say, we'll admit to it.
1.5, 6, okay, 7, okay, 8, 9, 10. Anybody on 11 yet? Ooh,
but I'm training.
That's good. Just out of curiosity, good to know. Back to this guy. Okay, so I showed you just quickly how you can create your own Docker image, and I have backup slides in case things didn't work. So basically what I said, build you can do ahead of time, you can package your image, you can upload it somewhere, and it'll be there when you need it, and run later when you actually want to run it. So that's the background of creating Docker images. The next thing we'll look into is how you can create your own JREs. So this brings us over to functionality that I said, as I said, we introduced in JDK 9 with Jigsaw. We had a challenge at the time, which was that the JDK kept growing and growing and growing. And part of the reason, or the reason, was that we kept adding great stuff to it. Things that somebody wanted. Not everybody, it turned out, but a few, a few people here and there, and we, went in and added some package somewhere, and JavaFX and whatever. And at some point, you start realizing that this is starting to become a really big big package, big runtime, big lots of like disk space if nothing else for unclear reason for most people. Now we did have the JRE, which was a subset of the JDK, so you didn't get all the bells and whistles that you got with the JDK, but you did get most of it, let's say. And we actually even had, and still have, I guess, for JDK, something called the server JRE, which contained even less stuff, but ignore that. So the full JDK, and these numbers have changed a bit recently, so keep that in mind. This presentation is from a year ago, and we've moved to this new release model where we actually have 2 releases per year. So it's almost hard to keep up with the presentation slides now, but it's mostly right, at least. I did go in and update the numbers, but roughly 600 megs for a Docker image where you have the base image, and I'll go into more about the exact details and the numbers here later, but the base image, so that's the Oracle Linux thing, and then the JDK on top of it. And that's 600 megs for running your application, which in most cases you'll probably only need a small part of. So we have all the stuff that you absolutely need. Java Lang, hard to get around without it. Java Util, management, whatever. But also some of the stuff that few people probably care all that much about. It used to be, maybe it was a good idea at the time or something, but Corba, I'm not sure about JAX WS, that may be more prevalent, but in any case. So what we did, and this work started, I believe, back in 2006 or something. We started looking at what's actually in the JDK and how can we try to modularize it? How can we try to split it up into smaller pieces and have those pieces build on top of each other? And what we ended up with in the end is a module graph, something like this. It turns out that there are cases where it's really hard to sort of cut out the pieces because we have weird dependencies where, yeah, let's not go into details, I guess. But in the end, we ended up with this module graph. So this is something that got introduced now with JDK 9. The goal here is that what you can do with your application is that in the end, you only depend on a subset of all this functionality. We have built, well, we've obviously modularized the JDK itself. Before I forget it, I should say you don't have to modularize your Java application. You still run it the same old way you did, and just leverage the modularization of the JDK itself. So we split this up, and we also provide tooling that you can use to create your own subset of this by saying that my application depends on only these modules. The tooling will then do the transitive closure computation on that and decide that, well, if you depend on that and internally we have these dependencies, we'll end up with this subset. And in the end, that's a much smaller, hopefully, runtime than you had when you started. This, I guess, is the summary of that. At the bottom, I should say as well, there's java.base. So that's a module you sort of can't, it's like Java Lang object. You can't run Java without it. It contains Java Lang and a few other packages. So I'm going to show you a quick demo of that as well. The demo gods are still with me. Oops. That demo would look like something like this. So in here I have a JDK 11, again released just a few weeks ago. In the bin directory you will find a couple of new commands. One of them is called jlink. Jlink is the command you use to create your own custom JREs. So you start out with the whole JDK and you can select which parts of it you want. The way you do that, and maybe I can start by running it, it will helpfully tell you that output is definitely one of the parameters you want. So I'm going to create my own JRE, and I'm going to put that in the my-JRE directory. I also need to say which parts to include, and I'll say, let's start simple. Let's only include java.base. So now you have the bare minimum, the smallest JRE you can create, which still can load and run simple applications. So as you can see, it did spit out a JRE, and it will look very similar to what you'd expect. It looks very similar to the full JDK. It has many of the same directories, it has many of the same files, but it is a subset. And just to prove that it actually still works, I'm going to run hello world, and it still runs hello world. Now, the obvious first question is, how do I know which modules my application actually depends on? Maybe I can manually try to figure that out. Good news for you. we have a tool for that. There is a command called jdeps. Jdeps allows you to specify, for example, a class. You can also specify a jar file, for example, but let's say I say hello world here. Oops. Basically what it will do is to list so hello world happens to live in the unnamed package, or sorry, the unnamed module. That means the application, in this case hello world, is not modular where. It's old style application and so on. It has a dependency on the Java I/O package, which lives in the Java base module. It also has a dependency on Java lang, which also lives in java.base. Now the nice part about it, new functionality in Java 10, I believe, is that you can also get that in a more condensed form. So now instead of having a long list, you have something that is easier to process on the command line. And if you know your bash voodoo, you can now do something like this, where you say, do the jlink thing, but instead of manually specifying the modules, I'll run jdeps and ask it to spit out the list of the modules. And hopefully it will produce the exact same thing that we just saw. And then I'll just do, whoops, this for completeness. Perfect. So what we started out with was the JDK. I mentioned that it's relatively large. It's 300 megs in this case. There are different package versions of it, but let's say 300 megs. And if you do this, if you create your own JRE, you end up with something that is 48, 49 megs in size, something like that, 48. So that's obviously much smaller. So let's go into a bit of why you would maybe want to do that and what else you can do. So I showed you this. You can create your own JRE, and the application does not have to be modular. You can still run it. Here's an example of running jdeps on Tomcat. You get a few more packages, but the storage is much, well, similar, let's say. I'm going to skip over the multi-stage thing, but I will mention that this Docker multi-stage functionality is very, very nice for doing exactly this. You can say, and actually that's what Steve did, I believe as well. You can say start with the whole thing, create, do exactly what I just did, but as part of the build step in Docker, and then you end up with a JDK that only contains what you want to know. That's a Docker multi-stage for the win. So let's talk a bit about optimizing size. And the first thing I'll say here is, it may not actually matter to you. If you have, let's say, an application that you rarely or never update, and you run it in a single place on the network, like you deploy it once on one machine, and you never touch it again, then size maybe isn't an issue. But if you have functions, lambdas, you update them frequently, you propagate them out to thousands of machines, then image size may well be a thing that you need to keep in mind. So let's see what we can do to optimize things. So we started with this. So I talked about the Docker base image. So this is the operating system stuff, and obviously depending on which exact Linux distribution you start with, it's going to be, well, have different sizes, but at least it's going to be sizable. And then on top of that, we added the JDK, and you can see here that the number here is 568 megs. This is again because my charts are now getting 1 year old. The JDK 11 JDK is just 300 megs, still large-ish. Part of the reason is we removed a bunch of stuff, that we separated a bunch of stuff out. So JavaFX is now standalone. You can download it separately. It doesn't have to be in the JDK. It was just a convenience to have it there, so to speak. Mission control, a few other things like that. Okay, so we have almost 800 megs of Docker image here. Impressive, but let's optimize it. First thing we'll do, being the engineers we are, we'll go back and have a look at this slide, and we'll see that, well, the green bar is the big one, the blue one is smaller, so let's start with the green one. That should be where we can gain the most, or reduce the most size. So what we can do, for example, is use the tooling I just mentioned, jlink, to create our own custom JREs. Chances are that even though this has all the cool functionality in it, you only need a subset. So why always drag this thing around? I have a couple of different examples in here. One is java.base, that's only the base module, only the minimum thing, the thing you absolutely need. I also have something called Netty. Netty is it's supposed to represent, let's say, a web service of some kind, a smallish web application. You may need a few additional modules, but it turns out that unless you have really weird dependencies, almost, you'll end up with something that is almost like Netty in size. And as you can see, the difference between java.base and Netty is actually not that huge, so keep that in mind. I'll also say that Netty here does not contain Netty, the application. It's just the JRE for running Netty, so to keep that in mind. This does not include your application, it's just the runtime, so to speak. Okay, so that's neat. We went from 568 megs down to 46 or so. And if we now go back and add the base image again, it looks more like this. So we'll have the base image, still same size, we didn't do anything with that. And we have java.base in this case, and again, Netty is slightly bigger. So that's cool. We've saved a lot, but surely we can do better. And the difference between the left bar here and the right bar here is the base image. In the first case, it's the full-fledged, much like the full JDK, this is the full-fledged Oracle Linux distribution. It takes all the bells and whistles, printer services, I don't even know what's in there, all the bells and whistles. There's another one called Slim. There are Debian Slim images as well. There's like, it's a concept, I guess in the Linux Docker image world, that you can tear out the things that people probably don't need. You can always go back and install things on top of this if you want to. So this is sort of the minimum, if you so will, distribution that still runs stuff, that you can at least use to get bootstrapped. So that brings us down now from, 275 megs down to 100 and something. So that's pretty nice. Now we're making progress. Went from 800 down to 150. Still a bit big for what we want to achieve here. So the insight is that in the end, if you're running Java, if you're especially in the Docker world where you're typically not running side processes, things like that, you're running your Java process and that's it. That it doesn't actually matter which base image you use as long as it still runs Java. So, cue Alpine Linux. Alpine Linux is a Linux distribution which prides itself on being security-oriented, lightweight. And the way it achieves that is by using something called the musl C library and a busybox. So busybox is a distribution or a packaging of the normal commands you'd expect, like awk, sed, whatever. It's one big binary. It's actually one binary that gets reused for everything. So the exact same binary is actually executed both if you run awk or sed or whatever. It just looks at what's the name of the thing I'm being invoked as and behaves differently. So that means that you have a very compact packaging of all the tools you need that day. And the musl C library, normally if you download Linux, in the 99% case, you'll get the GNU C library, which is powerful, let's say, contains a lot of great stuff. It's also large-ish at this point. So it contains more than is needed to run Java, for example. Musl prides itself on being lightweight, fast, simple, free, and correct. And in the end, if we can use that instead to run Java, then maybe that's something. So these two bars are the same that we saw on the earlier slide. So you have the base image for the full distribution of Linux. You have the one which is the slim version of that. Alpine almost doesn't register. It's 4 megabytes in size, and that's basically the musl C library. There's sort of nothing else in there. It actually has grown since I created these charts 1 year ago, so I think it's 4.4 now. Still small. So now we're starting to make really good progress, I'm going to say. We have a project in OpenJDK called Portola. We love puns. So by the way, somebody talked about concurrency of fibers. We have a project called Loom, which aims to implement fibers in the JDK. Portola is a it's a valley up in Bay Area, and Alpine Road leads to Portola Valley. So I did not come up with this. I am the project lead for this project, but the point is at least to provide a port of the JDK to Alpine Linux, or more correctly or specifically. We don't care on the JDK side that it's Alpine, it's the musl C library that we care about. So there is a project for this, and with all of that in mind, now we're sort of looking at container deployments and size. One of the questions I normally ask here is there any interest in Alpine, like a port to Alpine like this? Would anybody pick it up, run it, care about it?
The one time I tried it, you couldn't run Java 10 on it, so that was done in an hour. That's going to be my question, are you running Java 11 on it now?
So what we have done is built and delivered early access binaries of this. We have not yet published or picked up and support. We don't support, let's say, general available or binaries of this. This is because, let's say, you're skipping ahead, so I'm going to say any interest. The next question I have is anybody interested in helping maintain it? Because that's sort of the challenge here is we are trying to gauge the interest in this. We're also trying to see if there's anybody else in the community, in the OpenADK community or elsewhere, who would be interested in helping maintain it. Right now it's Mikael's hobby project. Twice a week I pull in the latest changes, I do a build and we publish it. But if we're going to actively start sort of supporting it, trusting it, we need to have more people helping out and also do some more hardening, run more tests on it, things like that. Let me know if you're interested or...
Well, I mean, do you know, like, is AWS and Lambda, they take an interest in this? Or, I mean, I don't know.
That's a good question.
You would think they would have an
Put them
interest.
up yourself. Follow up, yes. Okay, good. Okay, so now we have Hello World-ish, so or small Java application in 50 megs. So now I'm going to say that I'm starting to feel pretty proud of this, and on top of that, I'm going to say that there are ways of packaging the java.base only JDK so that it's even smaller. You can use an option, for example, called compress, which takes a few of the resources that we have, locales and stuff like that, and compresses them down. So that on disk footprint will be even smaller. I think you say, if I remember correctly, something like 5-10 megs. But there is then instead a runtime overhead in that when you start up, you need to uncompress all of that. So we can optimize this further. I'm going to go through these next few slides relatively quickly because we can do better. But I'm going to say that this is starting to sort of push the limits a bit. So this is mostly maybe an interesting data point. If you go in and look at that java.base only runtime we just created, what will you actually see? Well, you'll see effectively two files. It's the Java classes, or more specifically, sort of the java.base module, the Java classes, let's say even the java.base module, and it's the libjvm that I love to work on. So we've optimized the modules part. Now maybe we can do something with the JVM. So 21 megs of JVM is still pretty big. So what's inside of the libjvm? So this is a bit of voodoo, but if I went in and just don't trust these numbers, they're actually sort of incorrect, but they're still roughly representative. How about that? So I went in and tried to classify which files belong to which module inside of the JVM, not Java module, C, C++, internal stuff. So we have, runtime, C2, compilable, blah, blah, blah. The insight is that if you want to run Java in a fully compliant mode, your application will work perfectly, you will run correctly. You don't need a JIT compiler. You don't need to optimize code when you run. You can interpret the code instead. You'll lose the performance, but it will still run. It will still be correct. It will just take longer. So a few of these bars are exactly that. They're the compiler. We can tear that out. You sort of do need a garbage collector, but you don't need 4 of them or 5 or however many we have. So we have one for small footprint, but you won't get performance. We have one for latency, but not for large heaps. We have one for throughput. This was default back in still JDK 8. The parallel collector, and we have one that is trying to be good at everything, and that's called G1, or garbage first. Sorry, not that one. That one. But you don't need, as I said, 4 of them or 5 of them. So let's keep one. Let's keep serial. That's the smallest one that still does the work, but again, you'll lose the performance. And we'll ditch a bunch of other stuff that we probably don't need. Now we end up with something we call the minimal VM. We don't actually ship this. This is a data point, just maybe fun to keep in mind. So instead of having a 20 meg JVM that runs Java, we now have a 5 meg JVM that runs Java. And it runs it perfectly. You will still get, again, functionally correct executing Java, but you won't get performance. You won't get, like if the garbage collection happens to kick in, and you will probably see a pause, let's say, a significant one. And you'll also not get a lot of serviceability or debuggability tools. So again, don't use this in production. Your mother warned you about this. But if you were to do all of this, so let's take Alpine Linux, we'll take the java.base only thing, and we'll add the JVM on top of it. We can actually, theoretically at least, package Hello World in an even smaller container. So this is now 30 megs in size or something like that. If you do the compression thing, if you do the strict debug, and again, don't do this, you lose symbols. If you have a stack trace, you won't know where in the method it is, right? But you can get that down a bit further. So that's now actually less than 20 megs. I like to think that, again, going back to it, if you have a runtime that is 50 or so megs in size, and you add your application on top of it, maybe that's reasonable. There are even more extreme versions of this. We have something called Substrate VM from Oracle Labs. That we're looking into right now. So suffice to say, we're optimizing and looking into this, but this is one of the ways of cutting at least and optimizing it. Is that the best we could do? No, it's not. We can do even better. We can't do it on a per image basis, but now we can start cheating across running processes instead. So if you go back and look at what operating systems do, you'll know that they'll use shared libraries, like libc is a shared library. You have other native shared libraries. And the whole point with them is that if you have multiple processes reusing that same library, only one copy will be in memory, and it will be shared. There are two parts to that. There's the read-only part, which is trivially shareable, and there's normally a read-write part, which gets copied on write. So it starts out being shared, and if you start modifying it in your process, you'll get a copy. The insight here in the Docker world we're in, or the container world we're in, is that there will be a lot of instances running on the exact same machine, and you'll also likely see almost or the same or almost the same applications being run on that same machine. At least they'll share the J or E, probably, or, I don't know, you know the Java frameworks better than I do, like Spring Boot, maybe? Is that a framework? Yeah. I'm a JVM guy. Operating system shared libraries work for native data. We have Java classes, and we have something called class data sharing for exactly that. So this is the exact equivalent or the same theory as native operating system shared libraries, but for Java classes instead. This works on, like, in non-container environments on your normal machine. It also works across Docker containers, running Docker containers on the same machine. The finesse is, or the thing is, that you do need to store the archive. We call the file we store the Java class data in is called an archive. Historical reasons, I guess. So you do need to store that in such a way. You need to build your Docker containers or images in such a way that that file gets shared. But once you do that, if you have a Docker image that has that in it, then it will get shared automatically. Class data sharing will help you with the memory footprint, in that, again, you don't need two different copies of this data in the different processes. The nice part is that it will also help out with startup time. The reason for this is that the data we do store in that file is on a format that the JVM likes much better. It is, like, normally the first thing the JVM does when it sees a class file is morph it into whatever it wants to do, like the better format it wants to have internally, and throw away the class file. And that's basically what we do with this archive. We take the data, we massage it into a format we like, and we store that in a file. That process, the morphing part, is costly. So if we need to do that on every startup, then obviously that will add to the startup time. But by having done that already, we can reuse the archive, we can just map it into memory, and it will be there in a format that the JVM likes. Your mileage will vary, but you can see everything from no op, so this is basically running Hello World, let's say, in which case the improvement is pretty significant. Jetty, which is slightly bigger, you'll see in this case 17%. hello world, sorry, JFAS, so this is function as a service, 33%, let's say, and Spring Boot, Spring Boot, I even have it in my slide deck, 5%. So again, it does vary a bit on exactly what you're running. I will say that this slide is showing what happens when you put only the JDK classes in the archive. So if you have a big application, obviously that won't be in the archive, and therefore you'll not see the benefits for the application part of it. Now the nice part is that we extended class data sharing pretty recently to allow for putting application classes in there as well. And then you'll see something like this instead. You can look at the numbers. These are fresh off. I got them this morning from the team working on CD application class data sharing. So again, pretty significant improvements now, not only for the base module itself, but for your application classes as well. A lot of this you get for free. We are going to actually start shipping in the JDK default archive with the JDK classes. But if you want to run, if you want to include more of your application classes in there, you can do that as well. I'm going to skip over that and just go quickly mention a few things about what we've done in Java to recognize and honor some of the Docker concepts or container concepts. So this is sort of a summary slide. I do have a link in here. I'll try to make the slide deck available some way as well, or through the video maybe. You can have a look. My colleague wrote a really awesome blog earlier this year, and I recommend you to skim through it. That's really good summary of what I'm about to say. Being a Java runtime, we're really good at adapting to wherever we start up. So we'll start digging around and like how many CPUs do we have, how much memory, and we'll just adapt, make use of what we can, and all of that. That works well as long as we get the right numbers again. If the operating system lies to us, that's not going to work so well. And that turns out to be the case with Docker. It's sort of transparent, but only to a point. So a lot of what we've done is to go in and just look at the right numbers, instead of looking at what we thought was the right number and what had worked like 20 years before it. Now we need to look at something else as well. So that's a large part of what we've done. This comes down to memory, CPU, things like that. So once we started looking at the right numbers, that sort of automatically, this is something that the JVM does and exposes up to other parts of the runtime. So for example, if you for some reason called runtime available processors, we'll now show the right thing that Docker tells us to do. The fork join pool inside of the JDK also shows the right thing. We have a bunch of internal thread pools that also now used, and they're sized appropriately, I guess. And basically, if you the way you the way you ask Docker to say this is how many CPUs you're allowed to use is by using these options. There are a bunch of them, CPU sets and CPUs and things like that. Those didn't used to have any effect whatsoever. So in 9, I think we didn't honor them at all. In JDK 8 we didn't honor them at all. In JDK 9 we started honoring some, in 10 even more, and hopefully now with 11 that should all work. Same thing with memory. We also added a few options to control how much memory to use. There used to be something called max and min RAM ratio. It was something, at least it was really hard to reason about. So we turned it around and say, no, it's percentage instead, which most people like better. So small improvements there. And finally, I'll also say that a few of our serviceability and debuggability tools also needed to be updated. They play tricks and communicate through the file system. And since Docker now adds sort of a layer of virtualization in your file system, we needed to start training our tools to place and look at files in the right place. There's more to come in this area. We're constantly trying to keep up with what's going on in the Docker world and if there are any new concepts on the operating system level that we should take into account. Quick summary. If you start with Docker and just put the naive full JDK in there, you'll end up with a large image. That may or may not be a problem, but if it is, you can reduce it. You can use another base image, or you can create your own JRE. And again, the tooling is provided in the JDK itself, so it's very straightforward. I'm going to say to do so now. If you want to package Hello World in the smallest possible way, you'll end up with something ballpark 40 megs in size. And again, we're looking at ways of cutting that down further, but again, naively, I like to think that that's a pretty reasonable size. Class data sharing allows you to share data now across processes, and it also improves on startup time. And with the latest versions of the JDK, we now are actively looking at and honoring, again, the resource limits and the arguments that you specify to Dockers, that we only use this number of CPUs and only use the amount of memory that you actually want the Docker container to use. More happening, as I said, but with that said, Q&A. Yes?
How does JDEPs do on code bases that use reflection?
So I think there are complications around that. I'm not an expert on JDEPs, but I would imagine that that's a challenge, yes. I don't think it's. I don't think it will give you an exact, like, every single dependency, but rather a here's a good start sort of thing.
So there's a lot of code bases these days use dependency injection frameworks and all kinds of tooling that does a lot of. You'd need like a very vanilla code base to really use JDEPs.
That could certainly be true. That could certainly be true. Again, I'm not, maybe some Jigsaw person on my team would say, surely have a better response to that. I'm a mere user of jlink.
What are the maybe comparable other users on the AWS Lambda that you're kind of competing with? Is your size already much smaller or similar size to what the other sizes are you can achieve if you're using different layers?
So I haven't actually done a lot of digging around like what other people do in this. So Jigsaw in itself is obviously relatively new. So the whole jlink functionality is only a year old, and on top of that, I think the number of people who picked up JDK 9 eagerly, so to speak, was relatively small. I think we'll see that change. It's not like it was zero, but I think we'll see a much bigger uptake now with JDK 11 going out. So I think we'll see more of those numbers going forward as well. We do have a team at Oracle who work on function as a service framework called FN, the FN project. And we've been working closely with them to make sure that we take into account their use case with both the startup and the image size reduction. As a matter of fact, my colleague, the blog I referred to here, he is actually on that team. So Matthew Hilliard here is working on that team. But I don't have any good numbers on the other things that we compare with.
You skipped over, I think, the AOT slide, right? So GraalVM, and does that factor into this at all?
So yeah, I skipped over. I can just say it quickly. So I talked about class data sharing, which effectively takes the class data part. How should I put it? If you compare it with operating system native libraries, you would take the data aspect of it, so like everything that isn't executable code, let's say, and puts that in the archive. The other big part that we have in the VM that isn't Java heap, so to speak, is JIT compiled codes, the optimized version of the Java bytecode that you run. And AOT, we have experimental functionality to do AOT compilations. So basically, you take your Java application and you say, compile this down to native code and do that in a way that is highly optimized. And that obviously allows you to reuse the online JIT won't have to do the same amount of work at least. It turns out that you still want to do online compilation later because that's the way you can get the best performance. But at least it can start out in a better place. And obviously, by storing it on disk as a sort of shared library again, you can reuse the library and get the memory footprint savings as well. There are two reasons why we're doing this. The first one is because, well, in the end, we want you as users to be able to get the benefits I just mentioned, let's say. The other sort of nefarious reason for this is that we want to use it ourselves because in the JDK, in the JVM today, we have not one, but two compilers. And to solve that, we're adding a third. The third compiler here is Graal. It comes out of Oracle Labs, and it's a JIT compiler implemented in Java. That's brilliant. We want to use Java for our, like everybody else gets to get the benefits of running or implementing stuff in Java, right? We want to do that as well. Now the challenge is that running or implementing, a JIT compiler in Java means that now at startup, well, if the JIT compiler isn't already there, then we need to compile the JIT compiler, and that's going to take a while, so then you get the startup overhead, right? So one of the key reasons why we started doing this was to be able to pre-compile, to compile ahead of time the JIT compiler itself and bake that into an image and then reuse it. So that's the sort of the AOT story we're looking at right now. Most of the work in this area is going into the nefarious part of replacing our 2 compilers with one new one. And once we come out in the other end of that, hopefully we can make more use of this, or provide more of this functionality to end users as well. There are benefits to this, both in terms of startup and footprint savings, but not nearly as big, I'm going to say, as with CDS and all of these other things.
Okay. Oh, one more question here.
One last question.
Just feedback. I mean, you know, footprint and startup time has always been kind of the VMs. It's always kept it in a certain space, so it's just awesome to see innovation happening. It's really cool.
These, I will say that these performance numbers that are coming out now, and actually the CDS slides I showed you here, the startup time slides, the numbers, these are, as I said, fresh off the shelf. These are actually for a presentation for Code One next week, so you're getting sort of a preview out of one of those presentations. These are really impressive numbers. We're really happy. How many people here know who Charlie Nutter is? He's the JRuby guy working at Red Hat. And he loves this. He tweeted, was it yesterday or today, that the startup time improvements now, he's basically seeing this for JRuby applications. His favorite use cases, he's just seen a 50% startup time reduction. So he's pretty impressed by that also. So lots of good stuff happening here and more to come. There's a nice slide I did not include, which has the trend. That's future forward-looking, obviously, but the trend is pretty good when it comes to startup time. It's going down linearly, sort of. So. Good.
Okay, great. Thank you very much.